These angles are the same, as we already said. And actually trying to find out what that would be, well, that's its own kind of story, I guess you could say. So you'd have something like this going on, and then you could say, okay, let me see what's going on here. There is a 90-degree angle right here. If that's a 90-degree angle, we can actually find out all the angles under consideration here. So let me just give you that. So this is going to be the vector sum here. There's going to be symmetry here. I'm just trying to do this cold right now, guys. So let's just see if we got this. We can actually do this. Should be pretty reasonable to do. If you got this angle, you could get like an angle right here, for example. You call it alpha. It's as big as this angle right here. That's also alpha. What is alpha? Well, I could go the inverse, I could do a lot of stuff here. I could go the inverse tangent. This is r over 2r. Inverse tangent of r over 2r, that's the inverse tangent of a half, will give me alpha. And I can find what alpha is. Once I found what alpha is, right here, I can also put it here to find what the alpha is there. That's another, that's its own matter. Let's see exactly what we want to say here. So we're saying this right here, I'll begin to see why they didn't ask this question in the first place. You're looking at something like this. And once you figure out the angle, that's a 90-degree angle, as we said. If you find what alpha is, 90 minus alpha would give you this. And from there, I guess you could find a few things. So let me try to think here what the other one would be. The other one is this guy. That's also alpha. This is also a 90-degree angle. So there is a bunch we could say here, guys. We could say that for the alpha that we actually figured out there, let me just, some reason I'm not seeing this too good right now, but let me just see if I can see it. Alpha right here, associated with this, it's not too bad. This angle right here, from here to here, that's alpha. From here to here, 90 minus alpha would give you that. And kind of look at it that way. You can say 90 minus alpha, and we can call this guy right here beta on this side. So let's see here, got it there, we call this. So we could say a bunch of stuff here, I guess you could say. You could say here's 2 alpha plus this. You'd say basically that 2 alpha plus beta would be a 90-degree angle if you wanted to go there. So here's alpha, and maybe we could put this guy. I mean, this is definitely alpha, guys. Alpha there, but let's make beta just right here. 2 alpha plus beta would give me 90 degrees, and we could also say 2 theta. This right here, 2 theta plus beta. Let's just make sure we got that right, how that would actually work. Yeah, it sure works. I mean, this angle right here, guys, is 90 degrees. Right here is 90 degrees. Right here, 90 degrees. Theta plus beta, this guy right here, the alphabet soup of stuff here, guys. But this is beta. Theta plus beta would give you 90. Alpha plus alpha plus beta would give you 90. It's pretty interesting stuff in that regard. You know it, well, you tell me where this is going to go. I'm looking at this. 2 alpha equals 90 minus beta, and 2 theta equals, 2 theta equals 90 minus beta. Well, wait a minute. 2 alpha equals 2 theta, theta equals alpha. Okay, that was definitely quite the adventure, but here we go. We got this guy, he's going to be equal to the inverse tangent of this. When you get it, you're going to wheel and deal, and you're going to do all the stuff you know how to do. I mean, you're going to get, the way to do it is, let's not do it, but let's explain how to do it. You're going to get the resultant of these 2 vectors, you're going to get the x component of this guy, correct? You're going to get the x component of this guy, which is going to be that. And then you're going to get the x component of this guy, which is going to be that. Then you're going to get the y component of this guy and the y component of that guy, and you're going to get tug of war, and then from there you got it under control. Okay. Anyway, that's not a bad, it's neat, it's good stuff. So, with having said that, let's keep going. Let's go to 19. I'm sorry, let's go to 29. We had already done, again, a few of these have already been done, you guys, but I want to just, for the sake of, they're important enough, I think they're good enough, we can kind of look at it. Problem number 29, chapter 30. Would you like this chair by chance? Problem number 29 shows 2 current carrying loops with I1 equals 4 amps clockwise and I2 equals 9 amps counterclockwise, placed with their centers at the origin of the XY plane. If R1 is 10 centimeters, if R1 is 10 centimeters and R2 is 16 centimeters, what are the magnitude and direction of the magnetic field due to the 2 loops at the origin? If R1 is held constant, 10 centimeters, at what would R2 have to be for the magnitude of the origin to be 0? Okay, that's a good question. We've already I've done that in discussion, but let's, I say we do it again. Again, sometimes I'll be erasing some of the formulas I put up there. I'll try to put the main formulas up there. They're up here, they're of use to us. They're also pretty well summarized in the book, at the end of the book. Let's talk. Let me get this out of the way and let's take it, if we can. Washing these boards later, right? All right, so, okay, let's keep going with the discussion pertaining to this stuff, you guys. All right, for 29, you guys, let's get a decent drawing of this thing at least. I mean, the book's got it, in case I'm not quite up to par with where you'd like to see this thing done. As far as the drawing's concerned, let's at least look at what we can find here. We are looking at, here is a loop. Here is another loop. Here is the center. So here's, and this is R1 right here. This whole thing right here is R2. They're talking about the current I1, they're talking about the current I2. And again, they're saying A and B here. What are the magnitude and direction of the magnetic field due to the two loops at the origin? Okay, that's one thing. And B, if R1 is held constant, what would R2 have to be for the magnitude of the two to be 0? What's going on here? Well, to kind of make the long story short, I mean, go right hand rule, have your thumb go in the direction of the current, roll your fingers, bam, your fingers are hitting the board. That's the B field due to this guy. Roll your fingers here, have it hook around, the B field's coming out of the board. So B field in, B field out, there is a bit of a tug of war. What's going to be the magnitude and direction, either into the board or out of the board? You understand if circumstances are right, what goes in and what's coming out, here's the out, here's the in. They could be 0 if the mathematics is played right, and they're going to ask us that for the other scenario that we got going on there. Okay? So, with that in mind, let's go there. Well, I mean, there's a number of things here. They go a little more old school on this whole thing. We can actually look up the formula here. I think the way we had done it, we'd actually gone out, talked about it a little bit more rigorously. So let's kind of stay with that. We've done it. We know the following. We got this right here. Okay, Biot-Savart's law. Biot-Savart's law, B vector equals mu 0 over 4 pi. B vector equals mu 0 over 4 pi Q times the quantity B vector cross R vector over R cubed. In terms of magnitude, what are you talking about? Well, in terms of magnitude, we're talking about this. Yeah, I mean, like I said, we're not sweating this too much. We already took care of the angle. We'll figure out the directions. Let's talk about magnitude right now. The direction we'll figure out. So the V vector cross R vector is V times R. And wow, there's a lot here. Well, there's an R here and an R cubed right here. R and R cancels. You got R squared on the bottom, and that'll tell us a lot so far. So let's see what we got. We got this, and at the end of the day, we just got, very simply put, let me see here exactly how I want to write that. Okay, here we go. We've got that. And again, a takeoff from this, this right here in a sense, I mean, that right there implies, and we said this earlier, but maybe not quite as explicitly as we're about to do right now. Well, actually we did. We said it we actually basically said this before. Let's talk about it. I mean, this is dB vector equals mu 0 over 4 pi Okay, well, we've been there, done that. All of that, at the end of the day, guys, all of this is going to imply, in terms of just magnitudes are being concerned, there's got to be, there's a sign associated with this, and there's an R vector here that's going to cancel out, and I think we're okay. So we got this dl, so we got IDL sine theta, so let me just write it the way I wrote it in the notes some kind of consistency to it. I sine phi dl so we're looking at that. I mean, if this is kind of the way it goes, you know, they give some, they talk a bit here. So let me, I talk a bit here. Let me figure out let me try to tell you what I said vis-a-vis that. If we're going to say all of this, let's stay with this guy. And there's a B field created by each individual loop here, and the differential element of B field associated with each loop is something of this nature. So if we do the right kind of integral, you guys, we should be okay to find out what kind of a B field we're talking about. Now they already gave, you know, that you can look this up, but I think, like I said, the way I had done this, guys, I kind of wanted to show the argument as to what's going on here when we're going to do it. You gotta be careful, you know, or maybe we kind of luck out in a sense, so we don't have to be too careful, but if we are careful, we draw a very good conclusion. DL vector cross R vector. This is essentially how the R vector looks. The R vector looks something like this. That's kind of what an R vector looks like. And the DL vector I, is perpendicular to it. That's great. The angle phi under consideration is a 90-degree angle. That's kind of what I said in the notes. So if that's the case, well, that helps. That helps a lot. What's the sine of phi? Well, phi is 90 degrees. If phi is 90 degrees, the sine of 90 degrees is 1. So that's of interest. Let's talk. I mean, we can say a whole lot, I guess you could say. dB in that case, in those circumstances, u0 over 4 pi, u0 over 4 pi IDL, and again, this Biot-Savart's law is incredibly important, empirically derived through, I guess I was told, through hundreds and hundreds of experiments. They were able to derive, to come at, through empirical means, what Biot-Savart's law is, as we said. V vector equals mu0 over 4 pi times q times the quantity v squared cross, B vector equals mu0 over 4 pi q v vector cross r vector over r cubed. And like I said, if you want to do that in terms of current, differential element of current, dB vector is mu0 over 4 pi, and you got I dl vector cross r vector over r cubed. Huge significance. So we come here, we say, okay, well, we're making the claim, it's hugely significant. We got to here, it kind of simplifies. We can say that B for any loop associated with any circular loop is going to look like this. You're going to go from 0 to 2 pi r. I put a capital R there just to kind of differentiate between everything else that's going on there, depending on what kind of R you're talking about. It's around the loop now we're talking, right? So we got mu0, 4 pi I dl. You know, I is a constant. Guys, mu0, 4 pi I, r squared, they're all constants. They're all constants. Which means, in this instance at least, they're all constants as we talk about it. We talk about this, and you integrate from 0 to 2 pi r of dl. The integral of, the integral of dl is L evaluated between these two limits is 2 pi r minus 0. It's going to be mu 0 I see exactly what we're doing here. I wrote it, okay, I should have written it. Not a real big deal, guys, but you got to watch what the heck you're doing. At least make sure everybody's in agreement. The symbols are in agreement with one another. Well, at the end of this whole song and dance, guys, a whole bunch of stuff flies out of there. 2 goes into here twice, pi goes into here once, r goes into here r times. At the end of the day, it's looking like this. And this is where they're getting that derivation. I thought it was kind of important to show where that's coming from, you guys. It's coming right here. So we're looking at something like this. And that's it. I mean, from here on in, A and B, this is really the money right here, you guys. This is really the money right here. I mean, it's like there's going to be a B field going into the board. There's going to be B field coming out of the board. In these two scenarios, I'm going to do a tug of war, and whoever wins it, and we'll find out by how much they won it. And we'll just take it from there. Okay, so this is something to look at. Having said all that, let's clear this up a little bit for us. Okay, we ran to this conclusion at the end of all this. See what we got. I mean, you're looking at it. That's what we're going to work with. I mean, this right here is what's going to get us there. So at the end of all of that, we're going to say what's B net. Let's just do a tug of war, and we'll take care of like formal assertions as to what direction's all about. Let's say you know that one guy's like now we said now this guy goes into the board. This guy comes out of the board. Let's see what's what. The guy coming out of the board, let's call him positive. So if that's going to be the case, write it like this. I already saw me do that right hand rule to get this guy to work. And then the guy going into the board is this. You got it. I mean, at the end of the day, let's see what we can say here. We got this. In terms of kind. Again, all of this is in your notes, you guys, but I figured if you see it live, you know, I'd love to do all of these live. You know, I told you that day one, before the circumstances that arose. Much less possible as it is to do this stuff live now for obvious reasons. That's it. I mean, it's as simple as this. You're going to figure this out. They told you what's there. Again, you just got to know what direction things are going. Again, why did I do it in that direction, guys? I2, right hand rule. Curl your fingers, bam, the B field comes out associated with this guy's current. Here, right hand rule, B field goes in associated with this guy's current. Well, those, you know, so that's the setup for the tug of war that's going to take place. Beyond that, guys, you plug in the numbers here. Let me, let me not write all that down because you have it in the notes as well. This is 9 amps. This is 16 centimeters, which is 0.16 meters. You got to use MKS system of units for sure. 9 divided by 0.16, 4 divided by 0.10. This is 10 centimeters. Do the whole business here, guys. It looks like, like I said, the outside guy overpowers the whole situation, and it's coming out of the page. We got B net for this situation coming out of the page. Tesla. That's out of the page. We're going to say, we're going to say there's an X and a Y. we'll say the board itself is associated with the XY coordinate system. Out of the board is the positive Z coordinate system. So that's the K vector out of the page. All right, I mean, that's A. B, they're saying, can you make this thing happen to be 0? I'll tell you what, I'll give you the setup again. All this, the stuff, you know, all of what we need is of course in the notes, you guys, but let's look at the argument. You want B net to be equal to 0. You want what's coming in to be the same as what's going out, and it's, you know, add up to 0, so to speak. Well, you saw me kind of do this whole setup in a more abstract sense to begin with. Yeah, looks good to me. What does that mean? Well, it means a lot of stuff. I mean, when you're here, as you're looking at it, if that's all equal to 0, this guy's a constant. He ain't really doing much. That guy's a constant. These guys got to be 0. If you divide by mu 0 over 2, divide by mu 0 over 2 on each side, you're getting basically the scenario 0 equals I2 over R2 minus, you know, there you go. Wheel and deal. And let's see what we can do here, man. And let's keep going. I mean, there's a whole bunch you can do. I mean, the bottom line is you're trying to figure out what would R2 have to be for there to be no net B field. Well, we already know there's a net B field from the earlier proposition that was given to us. So obviously, I mean, there's a net B field, and it turns out it's a net B field in the positive Z direction. What does that tell you? Well, it tells me that I got to somehow probably back that guy up. If one of them's if the small one's at 10 centimeters and this guy's at 16 centimeters, my gut's telling me that thing's got to be expanded in some sense. It can't be as strong a B field. If that's going to happen, R2's got to be smaller. Tell you what, let me solve for R2. Do the algebra. Multiply by R2 on each side, and multiply by R1 on each side, multiply by R2 on each side, then multiply by R1 and divide by I1. That's going to make it happen. That's going to make it happen. Well, what's what? Here it doesn't matter if you use centimeters, meters, miles, fathoms, whatever you want. Here it doesn't matter because it's a ratio. As long as we got a ratio, the laws of physics are going to hold no matter what. But you got, you know, if you're given specific answers and you're starting cold and there's not some ratio being discussed, it's a different matter. It's a different matter. So what are you going to do? Well, okay, I mean, let's just do it. We're talking about the I2 is 9, the I1 is 4. 9 over 4 is 9/4. That's 2 1/4, it's 2.25, whatever. All right. 2.25. This guy right here is 10 centimeters. What's 10 centimeters times 2.25? It's 22.5. You're done. 22.5 centimeters. 22.5 centimeters. .225 meters. So, important. Remember, it was 16 centimeters initially, you guys. It was 16 centimeters initially.